Hello everyone and welcome back to another Better Daily video. Today we'll be starting Unit 5, Kinetics, and we'll be going over topic 5.1, reaction rates. My name is Borat Badbaki and I teach at the Salam Center of Irving. So what is 5.1 really about? Well, in 5.1 you can expect to find kinetics, rates of reactions, graphical representations of rates, and just a little bit of stoichiometry. So starting off with kinetics, Topic 5.1 introduces Unit 5, which is all about kinetics. Kinetics is basically the study of the rate of a chemical reaction, which basically means that kinetics studies what makes certain reactions take place and how quickly those reactions occur. And so that's what the rate of it is, like how fast it occurs. And so kinetics helps us understand why certain reactions happen faster than other reactions and how reaction rates are affected. And so this could be by catalyst, pressure, etc. Just there's a lot of things that affect reaction rates, and those will be explained later on in Unit 5. So, for example, through kinetics, we could compare iron rusting or the combustion of methane. When iron rusts, iron reacts with oxygen and water to make iron oxide, which results in discoloration of the metal, and this process could take hours or even days. On the other hand, if you bring a match to a balloon filled with methane, the reaction for the combustion of methane will occur almost instantaneously, resulting in the balloon exploding. Logically, it makes sense for rusting to take longer than combustion. But what's the real reason for the rates being so different? Like, if we just think about it, like, we're like, oh, it's rusting. Automatically, in someone's head, they know rusting isn't just going to happen right away. But fire, like a gas explosion, someone knows that's like an instant thing. But if you really wanted to understand it scientifically, kinetics helps us actually explain these phenomena and helps us understand like what caused the rates to be different and what caused these reactions to actually occur. And next up, we have rates of reactions. The rate of a reaction is basically how quickly a reaction occurs, which basically means how fast it goes from reactants to products. And to measure the rate of a reaction, we can observe the concentrations of the reactants and products. But how do these concentrations reveal the rate of reaction? As a reaction takes place, the concentration of reactants decreases and the concentration of products increases. So as the reaction takes place, the rate is decided by the rate of which products are formed from the reactants in a certain time frame. Since the reaction is basically just reactants turns into products, the rate of the reaction, how fast the reaction happens, is basically how fast the concentration of the reactants decreases to become the concentration of products. And so to find the rate mathematically, it could either be written as rate equals negative change in reactant, change in concentration of reactant over change in time for the rate of disappearance, and we'll get into that a bit later, and rate equals change in concentration of product over change in time for the rate of appearance. And you can see that the rate of disappearance is negative, while the rate of appearance is positive. That's because the reactants are decreasing as the reaction takes place. Next, we have graphical representation. And so we're basically representing the rates of reaction, but on a graph. And so on the y, we have plotted concentration, and on the x, we have plotted time. So this just means that as we progress through the graph from left to right, time is taking place through the reaction. And as we go up or down, the concentration is changing. It's either increasing or decreasing. And for the red line, we have products, which makes sense since the products' concentration are increasing as the reaction takes place. And the blue line is reactants since they are decreasing. And so, since we're finding the rate of reaction, the rate is basically equal to the slope of the graph. And we can see that the rate of appearance is, as mentioned earlier, change in concentration of product over change in time. And rate of appearance basically means the rate or how fast the products are appearing. On the other hand, we have rate of disappearance, which is basically how fast the reactants are disappearing. As you can see here, a dotted line, the products and reactants stop changing. Like their concentration comes to a standstill. They stop increasing or decreasing, and the concentrations have now become stable. They're staying at the same concentration. And what this basically means is that the rate of the forward reaction is now equal to the rate of the reverse reaction. And we'll go over this more later on in different units. But this essentially means that the reaction has reached equilibrium, because the rate of the forward reaction, meaning the rate at which the reactants are decreasing to make products, and the rate at which the products are decreasing to make reactants is equal. So there's no change in concentration. They're not fluctuating anymore, since the reactants are decreasing while the products are also decreasing, but the reactants are increasing while the products are also increasing at the same rate. And next we have stoichiometry. So sometimes the rate of disappearance of one reactant is different from the other, or the rate of appearance of a product is different than the other. And so this can be explained by the number of moles of each reactant or product consumed or produced in the chemical equation. Also, not mentioned earlier, but the rate of appearance is the exact same as the rate of disappearance, except the rate of appearance is positive while the rate of disappearance is negative most of the time. So if you had A was turning into B, then the rate of disappearance of A is just the negative version of the rate of appearance of B. And sometimes they're different as mentioned here. So for example, let's say we have A plus 2B turns into 3C. In this reaction, the rate of disappearance of A, just like for example, it's negative 0.2. And even though B is also reactant, its rate is not the same as A. That's because 2 moles of B are consumed for each 1 mole of A. And so this means that the rate of disappearance of B is twice that of A, which would be negative 0.4 in this example. And then on the other hand, since 3 moles of C are produced for each mole of A that's consumed, the rate of appearance of C is triple that of the rate of appearance of A. And so that would be 0.6. And since it's opposite, it's positive, while A is negative since it's appearing. And so we could see here, if plotted with multiple products, we could see that A turns into B plus 2C. So we can see that the rate of appearance is equal to the rate of appearance of B is equal to the rate of disappearance of A. But since 2 moles of C are produced for each mole of A, the rate of C is double that of A, as shown in the graph. And then we can also see here this is the actual stoichiometry. To figure this out, you could use some math and use some stoichiometry coefficients. And so here it's saying that the rate of A is negative 0.1. So you plug that in, negative 0.1 with the units they're using, times 3 mole B over 2 mole A. Since the equation they used for this had A plus 2A plus 3B. So the coefficients were 2 and 3. And so that results in negative 0.3 mole B over 2 LS, and that's the units they're using. And so that results in negative 0.15. Now let's have an example question. So D plus 3E turns into 2F is the chemical equation we were given. So when the chemical reaction above is carried out under certain conditions, the rate of disappearance of D is 2.5 times 10 to the power of negative 2 ms negative 1. ms negative 1 is the unit used for this rate. There are different types, there are different units that can be used, but that'll be explained later on in a different part of Unit 5. What is the rate of disappearance of E and the rate of appearance of F? So just looking at it, you can tell right away. If the rate of disappearance of D is 2.5 times 10 to the power of negative 2, and there's 1D and 3E, that means that E should be consumed thrice as much as D. So right away you could tell that just the answer for the disappearance of E is just 3 times the disappearance of D. And you could do the same with F. Since 2 moles of F are made for each mole of D, that means that the rate of appearance of F is just double that of the rate of disappearance of D. And we could see, if you want to plug it in and do the math, you could see here, for the rate of disappearance of E, it's equal to rate of D times 3 mole of E over 1 mole of D. Basically, just the coefficients. You put them over the other. So for the rate you're trying to find, you put that coefficient over the rate you know and multiply it with the rate you know. And so if you plug in the numbers, you would have 3 times 2.5 times 10 to the power of negative 2, which results in 7.5 times 10 to the power of negative 2 ms negative 1. And then the same you can see here for rate appearance of F. It just rate of D times the coefficient of F over the coefficient of D multiplied by the rate of D as mentioned earlier. And so that results in 5 times 10 to the power of negative 2. And so now here's a practice question for yourself. Hopefully you have solved it by now. If not, pause the video. The answer is D. And so the reason for this is that the initial rate of decrease in concentration of X, basically just meaning the rate of disappearance of X, was equal to that number, what was the initial rate of disappearance of decrease in concentration of Y? Basically, they're just saying what's the rate of disappearance of Y. And so right away you could see there's 2Y consumed for each X consumed, meaning it should just be whatever number is double the rate given for X. Thank you for watching. I hope you come back and watch some more for 5.2 and onwards. Have a great day.